It eliminated a lot of the interference. Can you still hear me okay?
Yep.
Okay. So the way this works is I have a drawing tablet, and whatever I write on my tablet, you should see that equation.
Yep.
And with algebra, pretty much most of the problems can be verbalized by you, and you verbalize the problem, I'll write it down, and then we'll attack it, okay?
Okay, sounds good.
If it's a problem such as, let's say they're giving you a piecewise graph and they want you to come up with the function, in other words, if it's something that's difficult to verbalize where I need to see it, you can take a quick picture of it with your cell phone and send it to my email address. And then I can bring it up on the screen and we'll both be looking at it. But maybe you don't have anything like that tonight, and everything we're going to cover you can verbalize perhaps. I don't know. But anyway, I'm also recording this. All of the sessions are recorded, and by tomorrow morning you'll receive a link so that you can watch the recording if you want.
Okay.
It's always the next morning because it takes my computer all night to process all my daily sessions. So keep that in mind in the future. You might want to make sure you have your tutoring session 2 nights before a test instead of 1 night.
Okay.
Because, if you have a test tomorrow, you're going to be up and off to school before you get this recording. So it won't do you much good. So that's the way the recording works. All right. So what kind of problems you got? What can we start with here?
Okay. Give me a second. I'm gonna try to connect you to one of my speakers because my phone speaker is broken for speakerphone.
Okay.
So I'm just gonna try to connect to one of my little Bluetooth speakers so it's a little louder.
So the audio is not so good for you, huh?
Yeah, I mean, I can hear you, but it's just kind of faint.
Okay. It's actually really good on my end. It's almost as good as it would be if we were using GoToMeeting and you had a microphone. You can pick up microphones pretty cheaply, like $10, $20. What's that? Yeah, I can hear you.
Okay, yeah, it's better now.
Okay. So, what problem should we start with here?
Okay, so right now we're doing simple or compound interest equations.
Doing what?
Simple and compound interest equations.
Okay.
And I'm just pretty confused on a lot of that.
Okay.
And then, so I'll just kind of give you like a gist of like what our test will be.
Okay. First of all, let's review those equations.
Okay.
The amount you have at the end of a certain period of time equals the amount you started with.
Yes.
Times 1 plus R to the number of years you're going to invest it. That's simple interest. Actually, that's yearly compounded, excuse me. Have you also dealt with problems that are more often than yearly?
So we have one question, so I'll read you this question.
Okay.
You found a stock fund that pays 11% annual interest compounded monthly to deposit your savings of $2,500.
Okay.
And then how much will you have in your stock fund at the end of 7 years?
Okay. So if it's more often than yearly, the formula is slightly different. It's the amount you started with times 1 plus the rate divided by the number of times you're going to compound it. Well, if we're compounding it monthly, that's 12. And instead of times t, it's times the number of times you compound it times t. So the second equation is what we use when we're compounding it more often than yearly.
Okay.
Now it's just a question of plugging in the numbers. So you said $2,500?
Mm-hmm.
So that's the starting amount. 1 plus 11% is 0.11. We're going to divide it by 12. And how many years?
7.
So T is 7. So all we have to do is solve that. Okay, now that, you have a calculator in front of you?
I just had it and then I misplaced it, so I'm looking for it right now.
Okay, when we have our sessions, you always want to have a calculator in front of you. Let's see, I've got my Inspire. What kind of calculator do you use?
Inspire.
Okay.
Yeah, I got it right.
You got it good. It's better if you do it on your end than me. Okay, so evaluate this middle part. In other words, that part there. Take 0.11 and divide it by 12 and then add 1 to it. What do you get?
I got 2.32.
You're taking 0.11 and dividing it by 12.
I thought the times 11. I'm sorry.
In other words, it's got to be a number smaller than 0.11.
Yeah, I got it.
What is it?
Wait, so you want just 0.11 divided by 12?
Yeah,
right?
what is that number right there?
I got 0.0091. And then 667.
Yeah, how many places you carry it out to might be important because we're going to exponentiate this number.
Yeah.
Okay, so we're going to take it to the 84th power. So the next step in your calculator is to solve this part. Take that. In fact, it's better if you use the answer because then you don't have any round off error at all. So take your answer that you came up with, add 1 to it, and then take that answer and raise it to the 84th power.
Okay.
What do you get? I'm guessing 2, somewhere in the neighborhood of 2, maybe?
Yeah.
What is it?
Yeah, whatever you got on yours.
I didn't do it on mine.
Yeah, my Inspire is dead, so I
Okay, all right. Here, let me show you what I've got. I have TI-80.
I know how to do all this stuff on the calculator, so don't worry.
Okay, I have a virtual calculator here, but it's a TI-84. Okay, so let's just make sure that you can do that process. If I take 1.009, I'll just do that part of it, and raise it to the 84th power. That's how you do it. And you do it the same way on an Inspire. Okay? And then if I hit enter, yeah, it's 2.12. So that's how much you're increasing your money by.
Okay.
Okay? So we still have to multiply that by 2,500. In other words, if you can get 11% on your money, it takes about 7 years to double it. Whether it's compounded yearly or monthly. Monthly is a little bit better. In other words, this turned into 2.21. So slightly more than double. And then multiply that by the 2,500 and you'll have your answer. Okay. Now, this can get a little bizarre looking sometimes. I mean, first of all, taking something to the 84th power, how often do you do that? Let's assume that it was 11% compounded daily. Now, how does that change everything? What number?
Well, so the next problem is compounded weekly.
Okay, let's compound it. Same problem?
It's the next problem. So it's how much money should be deposited into an account earning 6% interest compounding weekly in order to have $3,700 in 4 years.
Okay. So first of all, we want to write the general formula. This one right here. But it's not a 12 and a 12 now. You refer to that as K?
Yes.
Okay. So it's a K, K being the number of times per year that it's compounded. So help me fill in everything I need to fill in to solve this problem. Let's erase the 11%. That was the last problem.
So it would be A equals 3,700.
Not quite. Remember, there 3,700 is the amount that it became worth.
Okay.
So A equals 37. Well, that is what you said, but I thought you were saying it in a different way. This is what we're trying to solve for. How much would you had to have deposited for it to be worth $3,700 after 4 years at 6% interest? Okay, so this is my variable, the starting amount. What's the rest of it? This is 1 plus, what's R?
6%.
Okay, you can't use percents in equations, so you always have to convert that to a decimal.
Yeah, so 0.06.
Divided, what's K?
It's by 4 years.
Well, weekly means how many times a year?
So
52. K is 52. In other words, you don't count up the number of weeks there are in 4 years. You merely want to know how many weeks there are in 1 year, because we're going to compound it 52 times. Okay? And then that all goes, K is 52, 4 years. So now we have to solve this equation. Best way to approach algebra or geometry or any of them is to always start out with the general equation and then fill in everything that you know. And you're usually left with one variable that you can solve for. And we don't even need logs to solve for this. Have you had logarithms yet?
That's also on my test.
Okay. If, in other words, each of the problems you've given me so far, the thing to solve was on the algebra line. If the variable was up here in the exponent, then the only way to solve those kind of problems is to use logarithms. Okay? You cannot solve an exponential equation using algebra. If I tell you that 10 is equal to 3 to the x power, that's an exponential equation. It's not an algebraic one. And there's no algebraic way to solve it. In other words, I know x has to be greater than 2, but less than 3. But I have no idea how to solve it. But with logs, you can solve it. Okay. Now, what's the next problem? Did you want to cover logs tonight?
Yeah. So we have normal logs and then graphing logs, and graphing logs makes absolutely no sense to me.
Okay. First of all, let's talk about logs, because every discussion of logs requires you to begin with this. That is the exponential representation of that equation. There is an equivalent logarithmic representation of that. What is it? Do you know?
Say that one more time.
how do you convert this exponential equation into a logarithmic equation?
So it would be, so B would be the one, like the little number that goes by the log.
Right there,
And then the X is the exponent that goes right above.
That is the most important thing to remember about logs, is that logs are exponents. In other words, if I didn't know how to do this, I would start off with this. The log is equal to that exponent, because that's what logs are. And then all I have to do is figure out where to put the b and where to put the y. Well, like you said, the b always goes down there. There's only one place for the y, right there. So if I had 8 equals 2 cubed, and I wanted to write that logarithmically, what would it be?
So it would be, so log 8, well, so log.
I don't know what kind of terminology your teacher uses. The terminology I use would be log base 2 of 8 equals 3.
Yeah.
Okay. And the beauty of logs, the reason it was developed, is so that we could solve exponential equations where the variable is in the exponent. And you can see that some of these problems we have here is all I would have to do is reword them a little bit to put the variable in the exponent. In other words, let's say we started with $1,000 at this 6% weekly, and our t now becomes the variable, right? And so you end up with this equation to solve. Now, this equation is much harder to solve than the previous one, because this is an exponential equation and we do have to use logs to solve it. First thing I would do is divide both sides by 1,000, and then I would take the log of both sides. And then, using the rules of logs, you can bring the exponent and put it down on the algebra line. In other words, if I have 3 equals the log of 15 to the t, I can take this t and bring it down in front here. So that now I have 3 equals t times the log of 15, which is just a number. So now I can solve for t. T equals 3 divided by the log of 15. So when you have exponential equations to solve, that's when you use logs. And usually you take the log of, actually I needed to take the log of both sides here. In other words, for me to do this problem properly, I would take the log of both sides, then I would move the t down. So t is going to end up being the log of 3 divided by the log of 15. And that's how I would solve for t. But it always involves taking the log of both sides. Now, you don't always have to take the common log of both sides. You can take the natural log. I tend to work in natural logs all the time. Most calculators only had 2 keys on them, and that was natural log and common log. So you don't end up spending a whole lot of time doing other bases. But your Inspire actually has, you can do the log of whatever base you want. You don't have to use the change of base formula even. All right, you got another problem that?
Okay, yeah, so graphing logs.
Okay, you say graphing logs?
Yeah.
All right, let's talk about the basic y equals log of x. Okay, that graphs like this. This point is always 1, 0, no matter what the base is. In other words, all log functions go through that point, whether it's natural log, common log, or log base 17. And this is the inverse of the exponential graph. In other words, let me put it in blue. Logs are inverses of exponential. This function right here would be y equal 10 to the x. Okay, so that's a standard exponential equation, and the log equation always looks exactly like this, only it's reflected about the line y equal x. All inverses are. You've studied inverse functions?
Yes.
Okay. So when you come up with an inverse function and you graph it, it is always its inverse reflected over the line y equal x. In other words, this red line here is the reflection of the blue line across the blue dotted line. Okay? So in terms of graphing, this is just like any other elementary function. Y equal x squared is a parabola. Y equal e to the x is that exponential thing that rises real quick. You've studied undoubtedly the 10 elementary functions, y equal square root of x, y equal x squared, y equal x cubed. Each of these has a graph. Okay? And then, I don't know if you're there yet or not, but also you're going to study translations. In other words, when you have functions that are translations of the elementary function, then you can figure out how to move the graph. If this is y equal log x that I've drawn there, and I say, well, how do I plot y equal log x plus 5? Well, that's just a translation. I'm going to take this red curve and move it vertically, shift it up 5 units, which means this point goes to right there, 5, 0, or 1, 5. Sorry, a vertical shift affects only the y coordinate, not the x. And now we draw it roughly the same shape. It's just up higher. It's up by 5 units. And just an interesting piece of information, the log function is about the flattest function you will ever see. And by that I mean that if I go out 2 miles to the right, I will only go up by 12 inches. Okay? And it can look almost like there is a horizontal asymptote here. In other words, this thing is so flat that it looks like it might be coming up against the horizontal asymptote, but it's not. It goes up to infinity. In other words, if you go far enough to the right, this thing will keep going up and up and up. And so the log of infinity is infinity. Okay, it just would take an extremely long time to get there. All right, why don't you give me one of your functions that they want you to graph, and we'll try to graph it.
Okay, y equals log base 3 parentheses x minus 1.
Okay, so what's the elementary function? In other words, in order to figure out how to graph this one, we need to know how to graph the elementary function.
Well, so it asks for the parent function. Is that what you're meaning?
Yes, the parent function. That's what I mean by elementary function, the parent function.
Isn't that just y equals x minus 1?
No, it's log base 3 of x.
Okay.
Okay. this minus 1 that comes inside the parentheses, if I were to label this f of x instead of y, there's your parent function.
Yeah.
Well, this is a different function, but what it is f of x minus 1 instead of f of x. Let's go through this notation of the f notation. Let me start with something a little simpler. If I had f of x equal x squared, what would f of 3 be?
That'd just be 3 squared.
Correct. In other words, whatever's in the parentheses, you plug in for x. That's the rule. Okay. What would f of x minus 1 be?
Negative 1 squared?
No, I'm going to take, wherever I see x, I'm going to write x minus 1, put parentheses around it, and then square it. Okay? And because I have a shift inside my parentheses, this is a horizontal shift to the right. Okay? So I'm going to take the parent function, whatever that graph is, and I'm just going to not change its shape. I'm just going to move it to the right by 1 unit. Okay? Because what we're looking at here is f of x minus 1. In other words, if this was f of x, which was log base 3 of x, then f of x minus 1 is log base 3 of x minus 1. Okay? So let's graph the log base 3 elementary function, and the main thing we know is it goes through that point right there, no matter what its base is.
So it gives me a table of it's x and y, and it gives me 3 places.
Okay. So you have to put 3 points on that table.
Yeah, and on this test they don't let us use calculators, so we have to pretty much do this from our heads. Okay.
Well, so what's one very clear point that goes on that we're going to shift? In other words, what we have to do is we have to take this log base 3 of x, and we shift it 1 unit to the right.
Yeah.
Okay, well, clearly this point right here is going to get shifted to there, right?
Yeah.
So it's going to go to 2, 0. And let's figure out some other points here. What is the log base 3 of 3? Here, let me, just a second, let me do this slightly different here. I'm going to label the shifted points in blue. It'll be a little easier to see this. So the first point we're going to shift is that one. We're going to shift it to 2, 0. And let's find another point on the red curve. Well, when you're taking logs, the log base b of b is always 1. Okay? So an easy point is x equals 3. When x equals 3, f of x equals 1. So if I go out here to 3 and go up to 1, there's a point on my original curve. Let's draw the curve a little bit better. Let's see, that point is 3, 1. In other words, the log base 3 of 3, when x is 3, f of x is 1. Okay, so this curve, and this curve is asymptotic normally to the y-axis, and it's going to go through that point like that. So that's the original curve. That's the parent function. Well, what happens to this point, 3, 1, when I shift everything to the right?
It becomes 4, 1.
Correct. It only affects when I'm doing horizontal shifts, it only is going to affect the x coordinate. So 4, 1, whoops, wanted to do this in blue. So 4, 1 is about right there. Okay. So there's another point. So at this point, and what about our new vertical asymptote? Where is it going to be? In other words, our vertical asymptote with the parent function was x equals 0, which is the y-axis. Okay, where's our new vertical asymptote? If I'm shifting everything over to the right by 1.
That would be 1.
Yeah, so we're going to have a new vertical asymptote that goes right through here. And now, really, that's everything I need to graph it. Okay? And perhaps that should be your third point on your table, is the vertical asymptote. Because I know that the function goes through those 2 points pretty flat, and then it comes down and it goes to heads to negative infinity, always getting closer and closer to the asymptote. So that's how I would do it. I would use 2 algebraic points and the vertical asymptote. Now, this point 1, 0 that we got from the parent function, if x is 1, then f of x, the log of 1 is always 0, no matter the base.
Okay.
That's why all log functions go through the point 1, 0. Because the log of 17, the log base 17 of 1 is 0. So they're all going to go through that point. As far as finding one more point, well, what would the log of 9 base 3 be?
Wouldn't it just be 9, 1?
No, in other words, if I had, let me switch back to red because we're with our parent function. If I had the log base 3 of 9, what is that equal to?
Base 3 of 9.
It's equal to 2.
Okay.
And the reason is that 3 squared equals 9, right? In other words, you want to be able to go both directions here. If you have the exponential, you want to be able to do the logarithmic, but if you have the logarithmic, you want to be able to do the exponential also.
Yeah.
The way I usually do it in reverse is I take the number on the far left, raise it to the power of the number on the far right, and it's equal to the number in the middle. Okay? So, for me to find an easy point that I can do without my calculator, I'm going to use 9 as my x value. In other words, if I go on my parent function, there's going to be a point 9, 2. So there's my 3 points. 1, 0, 3, 1, and 9, 2. And what happens when I translate the 9, 2 point 1 space to the right? What do I get?
When you move the 9 over,
Yeah.
you get 10, 2.
10, 2, exactly. So the third point, if you need 3 exact points for your table, there they are. In other words, here, this point goes with that one. In other words, I've just moved everything 1 unit to the right. This point goes with that one. I've moved everything 1 unit to the right. And that one goes with that one. And then connect the dots. And when you connect the dots, you end up with, whoops, meant to draw it in blue. you end up with the flat one that goes through our 3 new dots. Okay?
Okay.
Now, the toughest part about translations is figuring out what's being done. Let me give you some questions and you tell me what's being done. What if I had, I'll use this same function, only this time I'm going to put a 4 there. And I'm going to have just x. What is the difference between this and this?
Well, there's a 4 in front of the log now.
Right. This one is 4 times f of x, correct?
Correct.
In other words, this is f of x, so we just have a 4 times f of x. Well, when you have a constant multiplying the function, what you have is a vertical stretch. Okay? And are these terms familiar? Vertical stretch and shrink, horizontal stretch and shrink?
Yes.
Vertical shift, horizontal shift. And the only other 2 things you can do to a function are reflect it over the x-axis or reflect it over the y-axis.
Okay.
Now, if I told you that I had a negative 5, well, hold it. Let's talk about stretches. Okay? In other words, if I take my standard log thing and instead of plotting this is that, I multiply it by, let's multiply it by 2 instead of 4 just because I can plot it easier. It means that every point that was on my red curve is now twice as high, right? In other words, if I had a point here, it's now up there. If I had a point there, it's now way up there. And so the effect is you have a vertical stretch. It changes the shape of the curve, makes it more vertical, not quite as flat. Okay? So when you have a multiplier in front of your function, that's what it does, is it vertically stretches it. If the multiplier is a number less than 1, then it vertically shrinks it. In other words, let's, instead of putting a 2 there, let's put a 1/2. Now, instead of the log function looking like it's red, it's going to look half as high. It's going to flatten it out a little bit. Or shrinking it, yeah. In other words, if the 2 terms you use are stretch and shrink, I like to think of them, if I have a parabola, let's say I have y equal x squared. If I stretch that, it does this, makes it skinnier. If I shrink it, it makes it flatter, like that. In other words, the bottom one might be y equal 1/2 x squared. The middle one, this one, might be y equal 2x squared. Okay? And so the stretch tends to make things more skinny. The shrink tends to make functions look more flat.
Okay.
Rather than going through all of, I could go through all 6 of them and give you examples of them. Why don't you give me the problems you have, and then we'll let you figure out what's going on. In other words, what's the next one after log of x minus 1?
You mean the next problem? For graphing?
For graphing.
Okay. Y equals negative log base 2 parentheses x plus 4.
Okay.
No,
so we got 2.
Plus 4. The x is below in the parentheses. It's just plus 4 at the end. Okay.
That matters. What's the plus 4 do?
Well,
what's it going to do to this curve right there?
It's going to give you a vertical shift up.
Vertical shift. Difference between a vertical shift and a vertical stretch is a vertical shift does not change the shape. It just takes the entire curve and moves it up by 4 units.
Okay.
What are the implications of that negative sign right there?
So that's going to be a shrink.
No. Negative signs are reflections.
Okay.
In other words, what this would be negative f of x if I just had this part of it. Okay? What it actually is negative f of x plus 4. Well, the negative in front of the function is a reflection about the x-axis. If it's inside, if it was there, it would be a reflection about the y-axis. And that would actually be f of negative x. So keeping straight where your negative signs are matter a great deal. Well, if I'm plotting the parent function, even though it's log base 2, doesn't look a whole lot different than log base 3. In fact, I can't even tell that it looks different. It's going to look like that. The only thing I know for sure is it goes through that point, 1, 0. Okay? Now, when you have multiple things that you're translating, always do your reflections first. And it does matter. In other words, I don't want to shift up 4 and then reflect. I want to reflect first and then shift. It won't always matter, but it will matter sometimes as to which you do first. And regardless of how many reflections, in other words, if I had multiple reflections, if I did have a negative sign inside there, now I have a reflection over the x-axis because of that negative sign, and a reflection over the y-axis because of that negative sign. But we'll take it one at a time here. So first of all, I want to reflect it over the x-axis, exactly what I'm looking at here. Well, how does that reflect? It reflects over the x-axis basically kind of like that. Okay? Still goes through that exact same point, 1, 0. Now, I just move everything up 4 units to take care of this, but I do it after the reflection. So, this point that it was at 1, 0 after my reflection is now at 1, 4. In other words, my new curve, my final curve, in other words, the first blue curve you see on there is just this part of it. I haven't moved it up 4 yet. Once I move it up 4, this point goes to here, and my new curve looks something like that. Okay? And
so,
go ahead.
From that equation, could you can tell the asymptote. So what would the asymptote be in that
Well,
equation?
the asymptote doesn't change if it's a vertical shift. The asymptote is
No,
still
I know that, but just by looking at that equation, what would the asymptote be? Because we have to be able to
x equals 0.
It'd be 0? Okay, that's what I thought.
Same as it is for this one.
Okay.
Okay?
And then
The asymptote is not reflected by the, or is not affected by the reflection either. The asymptote would get affected if I was doing anything horizontally. In other words, this was a horizontal shift, so it affected my asymptote. Notice you have to take logs of positive numbers only. You can't take a log of a negative number. So when I'm even looking at this function up here, I know that x has to be at least greater than 1. Otherwise, I'm going to end up taking the log of a negative number. So to begin with, and that tells you where your asymptote moves to. Since x has to be greater than 1, then I got to have an asymptote at 1 for this one. But not this one. The reflection doesn't affect the asymptote, and the vertical shift does not affect the asymptote.
Yeah.
As far as finding the 3 points, I presume that each one of these, they want you to find 3 points?
Yeah.
Okay. The very easy way to find points on log functions is to use, first of all, 1, 0 is always the first point. In other words, when x is 1, f of x is 0. But in this case, it's being moved up by 4 points. So that point, 1, 0, goes up to 1, 4. And even though the log curve is upside down because it was reflected, it doesn't really matter, because when I plug in 1 for here, this whole thing becomes 0 when I put x of 1 in. So the negative sign doesn't really affect that point. Okay? Now, what other good points for x are going to make it easy to solve for f of x, or y? We'll call this y over here. In other words, for your table, the obvious first point is 1, 0 becomes 1, 4. But what's another good one to use for x? The same number as your base. What is what is minus the log base 2 of 2? What did I say that was always equal to? The circled part?
2.
It's always equal to 1.
1.
It wouldn't matter if this was a 17 and that's a 17. It's equal to 1. That's why we chose it, because I know that's going to be equal to 1. So now the negative sign does matter, becomes negative 1. So when x is equal to 1, y is equal to what?
Say that one more time.
When x is, excuse me, I said it wrong. When x is equal to 2, what is y equal to?
2.
3. Here's what we have. We have minus the log base 2 of 2 plus 4. Well, that's 1. So now we have minus 1 plus 4, which is 3. Okay? So when x is equal to 2, y is equal to 3. For your table, up here, when x is equal to 2, y is equal to 1. But on your translated function, when x is equal to 2, y is equal to 3. In other words, let me make sure that I'm being clear here. Let me make this table. I'm sure that this is the table they're talking about. One of these probably says f of x, and the other probably says g of x.
No, it just says x and y.
Does it? Okay, that's fine. But we do need to know so when and the table is for this function, y equal minus log base 2 of x plus 4, right?
Right.
Okay, so the first point Oh, I see. So you don't need a table of both sets of points. You don't need a table for the parent function. You just need a table for this function.
Yes.
Okay. Well, plugging in 1, what's y?
It'd be 0.
Be 4. You're right, that part would be 0. But I'm still adding 4 to it. So it'd be 4.
That'd be 4. Yeah.
Plugging in 2 for x.
And it would be 6.
No. Log base 2 of 2 is 1, but there's a negative sign in it, so it's negative 1 plus 4? 3. Now, what's the next best number to plug in for x? It makes it easy. Think powers of 2.
3.
What's 2 squared?
4.
So let's try 4. What is minus the log of 4? What's just this part right here? In other words, what's log base 2 of 4 is equal to what?
2.
Exactly, because 2 squared equals 4. So now put the negative sign in it, and this becomes negative 2 plus the 4. So when x is 4, y is 2. Okay? And now you can graph that not as a translation, and perhaps she didn't want you to do these as translations. The fact that, now that I'm thinking about it, the fact that she wants you to do this table, she probably just wants you to find 3 points and connect the dots. Well, where are my 3 points? There's 1. There's 1 comma 4. 2 comma 3. And 4 comma 2. Connecting the dots, we know it's going to be asymptotic with the y-axis. There's your graph. And I didn't do it based on a translation or a reflection, although I could have. That would have been a way to do it without using a table. Because if I do it based on a translation, I really only need 1 point. I need that key point. That 1 comma 0, I need to know what happens to it, and then everything else kind of follows along with it.
Right. So, how would you define the domain and range?
Okay. The domain is always the allowable x values. Let's take the parent function. If you look at it graphically, you can always see domain from the graph. What can x be? Or what can't it be? A lot of times finding the domain is figuring out what x cannot be. Can it be negative?
No.
Can it be 0?
No.
So it's got to be greater than 0. So the domain is x has to be greater than 0. If I had a function like this, y equals square root of x, which starts right there and looks something similar to the log function, but it's a little different. What's the domain of that function?
Well, so our domain's just a little bit different. It has to be like an example would be like negative infinity to.
Okay, so that's interval notation. Okay,
yeah,
so interval notation for this function right here. It's not negative infinity. It's 0 with a parentheses to positive infinity. Infinities always have parentheses around. In other words, x can be anywhere in that interval.
Okay. So for the last equation that we did, what would that be?
Okay. This one right here x still has to be greater than 1. In other words, if we look at my graph, you can read the domain from the graph. It's only to the right of the y-axis. So my interval notation is still 0, and the plus 4 doesn't really affect my domain, so it's still that. The first one we did, this one here has a different domain. That x has to be at least 1. Because if x is less than 1 or even equal to 1, then we're violating, you cannot take logs of 0 or logs of negative numbers. Just like you can't take square roots of negative numbers. Okay? So if there are horizontal shifts going on, that's going to affect your domain. Let's talk about range. Is that part of your discussion also?
Yes.
Let's take the basic function. What's the range of that? Range is referring to the allowable y values.
Okay.
Well, read it off the graph.
For which one?
For
the second one or the first one?
This one right here, which is this function right there. Okay? And now what is the range?
Well, wouldn't it be negative infinity to infinity?
Very good. In other words, it is all real numbers. When you take logs of positive numbers, you can get negative numbers, you can get positive numbers, and there's no limit. This thing goes all the way to negative infinity, and like I said, it eventually reaches positive infinity on the upside. So the range on log functions usually is negative infinity to infinity. And notice that if I do any vertical shifts, like that last problem had a plus 4, which was a vertical shift.
Yeah.
Didn't really affect anything. Still negative infinity to positive infinity.
For the range?
Uh-huh.
Okay.
In other words, you can't see it from my graph, but this red part of the line keeps going down, goes below the x-axis, and if you go far enough to the right, on the x-axis, you'll eventually reach negative infinity on the y. Okay. So ranges tend not to be so much affected by any of these translations, because the range for log functions is almost always negative infinity to positive infinity.
Okay.
The domain a little different, but okay. Let's see. What time?
So before
8 o'clock.
because we have to go in like a second, I have one more question.
Okay. Shoot.
So it's not a graphs or anything. It's just like the question is evaluate the logarithms, and then we have to kind of like come up with an easier solution for them.
Go ahead. Give me one.
Log base 2 to 256.
The log base 2 of 256?
Yeah.
And what is that equal to?
Well, it just says evaluate the logarithms, and then in parentheses, you show all work.
Right. Okay. So the easiest way to do this is to make up a variable. I'm going to say it's equal to x.
Yeah.
And then I'm going to turn it into an exponential expression.
Okay.
So if I want to write that exponentially, how would I write it? Remember, it's the number on the far left raised to the power of the number on the far right equals the number in the middle. So now you have to figure out 2 to what power equals 256. Well, that's not that hard to do. It goes 2, 4, 8, 16, 32, 64, 128, 256. That's 2 to the 1, 2 to the 2, 3, 4, 5, 6, 7, 8. X is 8. 2 to the 8th power is 256.
Okay.
Okay? And that would be sufficient work to show. And whether you introduce the variable x or not, it doesn't really matter. In other words, if I'm looking at this expression, I know what it means. It means 2 to some exponent equals 256, right?
Yeah.
So I can still come up with 8 as an answer, even though it doesn't start off as an equation. I'm just more comfortable making it an equation and making up a variable because now I know how to express that exponentially perfectly. 2 to the x equals 256, and now I can solve it by, they're only going to give you ones that are easily solved. Go ahead and give me another one. I'll show you what I mean.
I'll give you the hardest one that's on our study guide. It's log base 6 of 216 to the x.
Like that?
Without the parentheses, though.
Okay. Well,
Yep.
I can take that exponent and move it down in front, right? In other words,
Yep.
that's exactly the same as x times the log base 6 of 216. Now, let's analyze that part of it.
Okay.
What power do you have to take 6 to get 216? And always know these are always going to be relatively small numbers, and they're always going to be whole numbers too. Otherwise, they wouldn't be giving them to you.
Yeah.
Unless it was a calculator problem, and then it might not be a whole number. But 6 cubed. 6 times 6 is 36. 36 times 6 is 216. So, I can replace everything in the circle with the number 3.
Okay.
There's my answer, 3x. I'll write it more conventionally. Like
Well, so how would you show your work for that?
Okay, I would do this. I would first of all say that that's equal to x log base 6 of 216. That's step 1. And then I would say log base 6 of 216 equals the number 3. Remember, logs are exponents.
Yep.
And so my answer must be x times 3.
Okay.
Okay? Don't get this x confused with the x that I introduced before. This is a variable that they've put into it from the start. I didn't use my x this time. I figured out that the log base 6 of 216 is the number 3. Just because I'm familiar with my squares and cubes of single digit numbers. At least up to 6. Okay? All right. Does that answer most of your questions?
Yes, it does. Thank you very much.
You're welcome, Zach. And good luck to you. I think I have your mom's email address. What is your email address so that I can send the link to you?
Okay, so lowercase z 06 lacrosse, and that's LACROSSE at me.com.
Okay. By tomorrow morning, I will send you a link to see the recording of this session. And, and as far as future sessions go, you can go to my website, digitalmathtutor.com. Let me just write it in case your mom, she called me. She may not have this one. I think she does. But if you go to that website, you can schedule appointments. I use a scheduler on there. So it no S, just digitalmathtutor.com. And it'll show you my complete availability and let you schedule the appointment. The next time we have the appointment, I will just text you the meeting ID number. I won't call you. because you already have the software on the computer, and so all you need is the meeting ID number to get into the session.
Okay.
All right?
Perfect.
All right, Zach, have a good one. I'll talk to you next time.
All right, perfect. Thank you.
Bye-bye.